Welcome to section 13.5, chain rule for functions of several variables. We will do that, and we will also see how to find partial derivatives implicitly, if you remember implicit differentiation from previous classes. First, a little definition. A dependency graph is a tree diagram like this one here that shows how variables are related to each other in a function. So if we have a function w, which depends on x and y, then we would start drawing the branches of the tree like that. And maybe x itself is a function of t and s, and y is a function of t and s. So this would be the tree diagram, the dependency graph in this case. So if x and y, on the other hand, are so if a function w is a function of x and y, and each of x and y are functions of t, then we would have dw dt equals partial w partial x times dx dt plus partial w partial y times dy dt. So what is happening here is if you take the derivative of function w in terms of t, you multiply along branches like this, and then you add and you multiply along branches like this, and you add these terms together. So in the example here, there's also a variable s. In here there wasn't, and that helps explain something. When do we use the d and when do we use the partial sign? We use d when that is the only variable possible. We use partial when there's more than one option. So here, partial w, partial x, we use it because we also have another variable we could differentiate with. On the other hand, since x and y are simply functions of t, there's only one variable we can differentiate with meaning at least, so it's dx dt. Okay, so here's an example. W is a function of x and y, x is a function of t, y is a function of t. So by using the theorem that is just above, or by making a little dependency graph, we can see that we get exactly this, and from here on it's just using derivatives from previous classes. So partial w, partial x, if we analyze this, we see the second term is going to be 0, and this term is going to be just 2xy. Times dx dt, so since x is sine t, the derivative is cosine t, and so on. After that, we can plug in t equals 0, because this was the requirement, so it becomes 2xy plus x squared minus 2y. So in the end, we get negative 2. Note that in this example, and others as well, we may say, so why didn't we substitute from the beginning? We could have said that w was sine squared t times et minus e to the t squared. You can also do that. Of course, you would get exactly the same, no problem. However, if we don't have numbers, or if we just talk about general functions, this is covering these cases. We can actually do some work with this theory when we can't actually plug in always. So here's an example with a function w of 3 variables x, y, and z. So the dependency graph would start with w, and it would have 3 branches to x, y, z. Then x is a function of s and t, y as well, and z is a function of t only. So x would have branches to s and t, y as well, z would only have one branch to t, and that can help us find partial w, partial s. I'm looking for all the paths from w to s. So I'm going to do partial w, partial x times partial x, partial s, plus this one here. There is no need to go through z, since z is not a function of s. So we can see these two paths written here, and then it's just a matter of applying the general rules from previous calculus courses. Partial w, partial t has one extra step, because we can go to t in 3 different places. Notice that for the very last one, we could write dz dt instead of partial z, partial t, since it's the only variable accessible. And dz dt is equal to 1, so this is why there's nothing here, it's times 1. So, just a reminder about implicit differentiation. When you take the derivative dy dx for an implicit expression, you always have to multiply with the inside derivative if the variable of differentiation is not x. So 2y, the derivative is 2 times 1 times dy dx, and sine y, the derivative would be cosine y times dy dx. X squared, no problem, is just 2x. So after we get there, we can group dy dx, factor it out, and divide by everything else, and we get dy dx equals 2x times cosine y minus 2. What we're going to see now is another way to find implicit differentiation, and it requires us to set up a function capital F of xy that is equal to 0. So in the example above, I would just move sine y to the other side, and I would say capital F of xy equals 2y plus x squared minus sine y, and that is equal to 0. So the chain rule for implicit differentiation states that after we've made that setup, dy dx is always negative capital F derivative with x over capital F derivative with y. So let's see a partial proof. If we set capital F of xy equals 0, and if we imagine that y is a function of f, then this means df dx is equal to 0. So here y is a function of s, y is a function of x, so we can write df dx because we only have one variable. But we can also look at the tree diagram and write it as partial f partial x times dx dx plus partial f partial y times dy dx. Now dx dx is equal to 1, and that is equal to 0, so by moving things around we get what we were looking for. Dy dx equals negative partial f partial x over partial f partial y, and that is what we will use in the example below. So to find dy dx, I first need to set up my function capital F equals 0. It's always a function that is equal to 0, and after that it's a simple procedure. Dy dx is going to be negative the derivative in terms of x, which is just minus 2x. With the negative sign it becomes plus 2x, and the derivative in terms of y is 3y squared plus 2y minus 5. And there we have it. You could also do it, of course, with the previous techniques, and you would get the same answer. But again, it's a nice formula that we have here with this new theory. Thanks for listening.